Hi guys, and welcome to Mindset Learn Extra. This is grade 10 science, and tonight's show is brought to you by Liberty. Last week we covered chemical bonding with Tracy, and tonight our topic is transverse pulses and waves, and Tracy will be taking it through it.
Hi everyone.
So, okay, guys, a few starters. Please only send us questions relating to the topic that we're talking about, and if you stick with us throughout the year, we will eventually get around to the section that you're having difficulty with. Next week, our topic will be longitudinal waves, and lots of you have been asking us about our schedule. So, if you are in a group, the next topic next week is longitudinal waves, so write that down. The show tonight will start off with a lesson on transverse pulses and waves, and then after a break, we'll work through an example or two. Lastly, we'll be tackling your questions, and there are lots of ways to get hold of us, guys. You can Facebook us on www.facebook.com/LearnExtra. Our Twitter handle is @LearnExtra, and that's with an XTRA. So while you're watching, shoot questions off to us, and we'll get round to them in the third part of the show. I have a calculator to give away tonight. It's one of the best posts on Facebook. We will be announcing the winner on the page tomorrow. And after the break, we'll be announcing the winners from yesterday, as well as going through our lesson for the day. So guys, don't leave your seats. We'll see you now. Hi guys, and welcome back to Learn Extra Live. I know we're going to have an awesome lesson today, guys. So if there's anything that Tracy is going through that you're not quite understanding, please let me know on Facebook or Twitter, and I'll get Tracy to answer all of your questions. Okay guys, I think the best thing to do is go straight to Tracy. Take it away, Trace.
Thanks, Indiana. Well, actually, grade 10, I really like this section, I have to be honest, because you all have these wonderful ideas of what you think waves are and what pulses are, and we get some really nice terms. And in terms of your physics for your senior science, this is where we start actually getting into the fun stuff of physics. What you did in grade 8 to 9, it's okay, but this is so much more better. That was brilliant English. I think I should teach English. Anyway, so at home, you're sitting there going, no, hang on, wait, we're using the word wave. I've heard that before. Hang on, wait, we go to a cricket match or a soccer match, and the match is a bit boring. The crowd starts to do the Mexican wave, and we all know what that means. It means that people, as it goes around the stadium, people stand up and then they sit down. And actually, it's a really good example of a wave, and it's actually a nice example of the wave we're going to look at today. Or we think about at the beach, if we go to the sea on holiday, or if we're lucky enough to live by the sea, we know that we get water waves, and the waves crash onto the shore, and when it's a really scary day and there's lots of storms and stuff, it gets a bit scary, but we all know that there's waves, and we all know it has that nice motion, okay? Now that's also the type of wave we're looking at today. But when we look at those two, the water wave, and we think about the Mexican wave, they both have to have something to travel through. So the water wave travels through water, whereas the Mexican wave travels through people, okay? And the people in the water are what we call a medium. Now you're going to hear this quite often because this is very important for when we get to light, okay? Now a medium, and I've got the definition for you, is the substance or material in which the pulse will move. We're looking at a pulse at the beginning to start off with, okay? So it's what it needs to move through. Not every type of wave needs a pulse. Needs a medium, which is actually what makes light so exciting, but we're going to get there a little bit later, okay? Now, a pulse is where we need to start, and a pulse is a single disturbance. So when you were little and you played at school and you played with a skipping rope, okay, a good example of a skipping rope is, especially the boys, I'm pretty sure you would have done this just to annoy your friends who were girls, is they're holding one end, you're holding the other, and you shake your hand up and down, and then it goes all the way down, and then they get a fright if they weren't paying attention, or it gets it ripped right out of their hands, and you think it's hysterical, okay, and I'm sure probably some of you still do that, okay? That's a single pulse, because you're not doing it the whole time, you're just putting your hand up and pushing it down, and it causes this motion through the skipping rope, okay? I am hoping that some of you have used slinky springs at school, okay? Those are the little, it almost looks like a ridiculously long bracelet of metal coils, okay? And in fact, to put it into something which you might have seen in Toy Story, the very first one, the dog, the little sausage dog, he was a slinky spring in the middle, okay? He had the slinky spring in the middle. And often, if you go onto YouTube and stuff, if you Google it, I'm sure you'll find it, you can get those videos where you see the slinky spring jumping down the stairs. Okay, my learners get very upset. We can't do it at our school because our stairs are actually just too wide, so our slinky doesn't make it. It gets about one step and then it stops. Okay, that's just another example of a medium. But if I only disturb the springs once, it's called the pulse. Okay, now I've got two ways that I can disturb that. I can either push the spring up and down, okay, which is like the motion you see in the Mexican wave, or I can push it forwards and backwards. Okay, now if I push it up and down, it's what we call a transverse pulse. Okay, now I've got some important words here that you're going to need to know, and I'm hoping they're not too new for some of you. And the first one is perpendicular. Okay, like you learnt in maths, perpendicular means that they're at right angles to each other. Okay, and it's perpendicular to the direction in which the pulse is moving. Okay, we think about the example with the boy and the girl with the skipping rope. He pushes his arm up and down, okay, but the pulse moves away from him, okay? So if I'm looking at it this way, his arm's going up and down, but the pulse is going this way, so it's in two planes, okay? They're perpendicular to each other. This is very, very important. Now, unfortunately, the diagram I have didn't come out too well, so I'm going to try to draw over it because hopefully it'll make it a bit easier for you. But what the diagram is a hand on a slinky spring. I know you can't see it, but let's just pretend. And the slinky spring is here, okay? And it's moving up and down, and then, so this represents the coils, and the disturbance is this way, and then we get a little bit further on to the coil, and what we see is it's still going up, and then it takes a bit of a dip and it goes down. Okay, so that's a really bad diagram, but it gives you the idea. So the pulse, okay, is moving in that direction, the energy from the pulse, but it moves up, and then it goes back, and then it's moving up. So these two are, so we have that direction and that direction. We have a right angle to each other, okay? Now, what is really, really important about a wave? A wave is a way of us to transfer energy from one point to another, okay? That's what's happening here. We've given the slinky spring energy. We moved it. That energy gets transferred from one part of the slinky to another as it goes along, okay? So we're moving energy. That's the direction it moves in, and then it moves up and down. Single pulses don't actually help us very much, okay? They really don't. They're not that useful. It's one disturbance. What is useful for us is a transverse wave. If I have a series of pulses that are regular and repetitive over and over and over again, I get a transverse wave. Now, transverse wave is important, so it's the first one we're looking at. Light is a type of transverse wave. Water is a transverse wave. The Mexican wave is a transverse wave, so it's actually quite nice. And it's a form that you see quite often. But the difference between your transverse wave definition and your pulse is that this is a series of pulses. Okay? It's a series. We have lights. But what's important about a transverse wave? Well, the nice thing is a transverse wave ends up looking like the disturbance. Okay? So here I have what we call a wave form. Now what I'm going to do, guys, if you want to follow me, is I'm going to write a whole bunch of important terms on this diagram. You're going to have seen this often. You probably have seen this in books, the ways of representing sound, all sorts of things. But this is a wave form. What you're also going to see a little bit later, you wouldn't have seen it yet in your maths, is this is actually what we call a sine graph. It's the same shape as a sine graph, okay? Now, what's important about this? Well, there's first of all, there's some important places on here. Number one, over here, this is my rest position, okay? Or it's sometimes called the equilibrium position. Now, what we mean by that is this represents the position. So if this was a string, the rest position represents the place where it would have been flat before it got disturbed, okay? Then it gets disturbed, and we get a maximum from the rest position to a top part, and we get a maximum from a rest position to a bottom part, and that maximum's got a special name. It's called the amplitude. Okay? The amplitude. So that tells me how far it goes from the top to the bottom. But these bottom and top parts have important names. So when it goes to the top, we call that a crest. When it gets to the bottom, we call, not the bottom, we call it a trough. Okay? That's called a trough. Okay? And probably the easiest way to try and remember that is if you think of in a farm that the animals eat out of a trough. It's like a bowl. Okay? And the crest is the top of the wave, and if you've ever seen anyone do surfing or that sort of thing, they like to ride the crest of the wave. You want to be on the top part, not the bottom. Okay? So this wave has 1, 2, 3 crests, and it has 2 troughs. Okay? That's all well and good. It's different positions of our wave. But that doesn't really help us much, because when it comes to waves, we want to put it in terms of real physics, which is things like how fast is it moving, how long is the wave, how often does it come, how long can I expect it? Because pretty much the world around us is determined by sound waves and what we call the electromagnetic spectrum, which we're going to get in a couple of weeks. So it's actually quite important when we do this. So now, first thing I want to talk about is what we call points in phase. Okay, so we're looking for points that are in phase. Now, this point here, and this point, those are 2 points that we call in phase, because they are going to do exactly the same thing at exactly the same time. In other words, here's my point as my wave, and hopefully you'll see it I'm hoping they'll move if I hold them. No, they're not going to. Okay, so anyway, these points are going to move up together, then they're going to move down together, then they'll go down, and then they'll go up. So they're going to do exactly the same thing, which means over here, I have another point in phase. So I have those 3 points. There are hundreds of points in phase on any wave. Okay, that doesn't change. But we need to make sure that we understand where they are. Any other point on the graph, so if I now say, over here, this point here, this first yellow dot, and this yellow dot, they are not in phase, okay? Because my first yellow dot's going to go down, but they both is going to go down a little bit, but then this one starts to go up, and the other one's going down, and they're not following the same path. They are not in phase. They are what we call out of phase, okay? They are out of phase. But why are points in phase so important? Because they give us the wavelength. Okay, now we're going to get to our first Greek symbol. I think it'll be the first Greek symbol that you would have met so far in grade 11. Okay, so I'm going to choose 2 crests because it's easier. So this point and this point are in phase, and the distance from here to here is what we call the wavelength. Okay, now watch carefully. Wavelength's got a special symbol. It looks like an upside down Y. It's pronounced lambda, okay, and this represents wavelength. Now your wavelength can be measured from any 2 points that are in phase. Generally speaking, we'll take it from the top of 2 crests, we'll take it from the top of bottom of 2 troughs, or from the beginning and end of a wave. But they've got to be 2 points that are consecutively in phase, okay? Oh, and I've just got some extra little I'm not really sure what all of those little extra dots are, but these 2 points in phase have to be one after the other. Okay, so in other words, what I'm saying to you, grade 10s, is the top of that crest and the top of that crest are in phase, but that's going to represent 2 wavelengths, okay? And how do you remember this? Is you go, well, if I'm going to have 2 points that are in phase, then it must make the wave shape once, okay? And from here, let's make it so you can actually see it. From here to here, that's actually one wave shape. We just started in the middle. It starts at the top, goes all the way to the bottom, comes back up to the top. That's one wave, okay? Now, wavelength is a distance. So, thinking back to what we know, what would wavelength be measured in? And I'm hoping you're all screaming at the TV. Meters. Very important. We are going to deal with waves that are extremely small, where your wavelength is in nanometers times 10 to the minus 9. Even smaller, we can go to picometers, which times 10 to the minus 12, which is microwaves and that sort of thing. Or they can be very, very long, where they run into the meters, and radio waves do that, okay? So there's no wrong or right to this. There's no set thing that you can say, well, if I get a very big number, then I'm right. If I get a very small number, then I'm right. You can't do that. Amplitude's the same. Amplitude is also measured in meters, okay? And amplitude is a function which just really tells you how much energy. I think it's a good way to put it. So when you look at water waves, as they come onto the beach, they have a small amplitude. But if you look at the waves when there's a big storm, or the ones they use for surfing, big amplitude. Tsunamis, when they talk about a tsunami that then hits in a country, a lot of the times the issue is actually the amount of water that's traveling, because there's a lot of energy, and the waves are stories high, like probably the height of your school building or more. So it's got a huge, huge amplitude. And normally waves with a big amplitude have lots of energy. Okay, we're going to deal with sound in a couple of weeks as well. And amplitude tells you how loud something is. So when I'm talking really, really softly, I have a small amplitude. When I'm talking really loudly, like I do in my classroom most of the time, it's a big amplitude. But we're going to deal with that a little bit later. Okay, now we've covered the important parts of a wave. So we know what a wavelength is. Make sure you can define it. We know where our amplitude is, our rest position, and in and out of phase, okay? Please note, grade 10s, we don't actually have a set symbol for amplitude. So you don't make up a symbol. You're going to have to write it out if they want you to calculate it, unfortunately, okay? So what does that get to? 2 very, very important properties of waves, okay? Number 1, the period of the wave. First thing you have to take note of for me, and I'm begging with tears in my eyes that you get this. The symbol is a capital T, not lowercase t. A little t means time. This is very similar to time, but it's very specific. And a period is the time it takes for one wave to pass a point. In other words, I have a fixed point. Okay, we have a fixed point over here, and I have somebody watching, and then they go, well, here's my wave. How long does it take for that shape to pass that point? 1 wave, okay, measured in seconds. Frequency, which is a little f, not capital F. It can't be a capital F because a capital F stands for farad, which is a unit of capacitance. You're going to do that in grade 11, okay? Now, frequency is the number of complete waves that pass a point in 1 second. So once again, we have 1 point, and you have somebody counting how many of these waves go past that point in 1 second. So they go to sit and count, and they go to stopwatch and go 1 second. I counted 3, or I counted 4, I counted 7.5, whatever the case may be. Period, time for 1. Frequency, the number in seconds. Frequency's unit is hertz. Hertz means per second. Now I know you've heard that word before. Because when we look at our radio stations, okay, radio stations are found by their frequency. What band are they on? All right, and some radio stations actually give their name based on their frequency. And often when you look at the advert for a radio station, they tell you what frequency you can find them on. It is on megahertz, but it still hertz per second. That brings us to two important equations. Now, grade 10s. You may or may not be given these on your information sheet, okay? And I know for my kids, I wouldn't give them this in their first test because I'm just mean and horrible. It's a very important relationship. Frequency is equal to 1 divided by period. Period is 1 divided by frequency. They are the inverses of each other. So often in a calculation type question, you will be given period and you will need to find frequency, or you're going to be given frequency and you're going to be asked to calculate period. They come up a lot. Please make sure you write it down correctly. There's no shortcut to this one, I'm afraid. Okay, it's just one you're going to have to learn. One more thing before we go to a break. Okay, the wave equation. Now, the wave equation, I love the wave equation because it's really simple. What the wave equation says to us is if we take the velocity of our wave, it's going to be equal to the frequency of the wave multiplied by the wavelength of the wave. And it's the same for all of them. What's really important to note in this section is often velocity is interchangeable with the word speed. It's not 100% correct to do that because velocity refers to what we call a vector must have direction, whereas speed doesn't. But it is accepted within the scientific community that we can just interchange the two. Okay? The wave equation is nice if we're given frequency and wavelength, though sometimes we're not. Sometimes if we look at the information, we go, well, I don't have any of that. What do I do? We can also do this. If we remember that frequency is 1 over period, okay, that means if I've got the period, I can go, well, that means my speed is 1 over period times by lambda, which means that I could actually do this, which is lambda divided by period. It's another way of looking at it, okay? So it's another way of using the equation, but V equals F lambda is the official wave equation. Another equation we're going to use quite often is the fact that we all know that speed equals distance divided by time. Now that's going to depend on what information you're given, though we're going to steer away from those type of questions for now. Okay? So I think it's a little bit of an information overload, Indiana, and that's where I am, but I've got a couple of questions which we'll do.
Fantastic.
Just now.
Guys, I think what we're going to do is we're going to take a short break. I just wanted to let you know, while Tracy was talking, I posted a diagram of wave properties on the Facebook page for you that you can download to your cell phones and keep all the time so you can learn about the crest and the wavelengths and everything straight from your cell phone. I also put a diagram of the transverse waves. I found the exact one that you've got with the slinky. So hopefully they'll be able to see that better. So guys, visit our Facebook page, download them. We're going to take a quick break and we'll see you straight after. Bye. Hi guys, and thanks for joining in. We are back. I told you it was going to be a quick break. I hope you're all really enjoying the lesson because I am, and I'm learning lots and lots. I just want to give a quick wave to Anele and Kanisile and say, so glad you're joining in. And guys, just drop me a line. Let me know that you're watching on facebook.com/learnextra. Chat to me on Twitter @learnextra. My name's Indiana and I'm here to help you along the way. I know Tracy is chomping at the bit to carry on with her lesson. So Tracy, take it away.
Thanks, Indiana. Well, actually, I've got some really nice questions.
I know you do. I know you're super excited.
It's quite sad. My kids laugh at me all the time, but it's okay.
No, it's good. Exciting is good.
Now, what are the type of questions you can expect? Obviously, we can't cover all of them, so I'm going to cover the ones I think you guys struggle most with. Now, the first one here is one where it says, consider the following transverse wave. So we have a transverse wave function. Then it says draw the following. Now what would happen in a test or an exam, grade 10, is they would ask you to redraw this and then put the next sort of things on it. So please redraw this and label it as the original line, because if your teachers can't see the original line, then everything else you draw on it doesn't make any sense because there's no reference. Okay, because remember, this represents a wave. So this represents a wave with a specific frequency, with a specific period, wavelength, amplitude, and what we're asking you to do in this question is change those factors to suit what the question says. Now, what I'm going to do is I'm going to do them in different colors so that hopefully you'll see it, and it might get a little messy, so we might write some of them off as we go along. Now, the first question is, we're going to draw on it. It says, draw a wave with half the amplitude of the given wave. So the only thing that's changing is the height to which the wave goes. The wavelength is the same. So if I draw this one, let's do this one in green, okay? It still starts at the same point. It's going to go to half the height, or not. That wave went somewhere funny. It's going to go to half the height. It's got to reach the rest position at the same place. And let's. Okay, you're going to have to protect. I'm going to have to a little bit faster. Half the height, same rest position. Half the height, same rest position, or not. Okay, half the height, same rest position. Half the height, same rest position. Okay, half the height. I'm just doing it this way so that I don't have to keep redrawing from the beginning. But half the height. The rest positions are all the same, okay? It has a crest when my original wave had a crest. It has a trough when my original wave had a trough, okay? Hopefully you all got that. Second one says, a wave traveling with twice the frequency. Now we go back and we've got to say to ourselves, well, what does it mean when they say frequency? Definition we learned earlier, frequency is the number of waves that pass a point per second. So if I'm making the frequency twice what it is, that means I must have twice as many waves in the same time period. I'm not changing amplitude. Frequency and wavelength are very, very closely related. Remember, velocity is wavelength multiplied by frequency. I haven't changed the speed. I said nothing about the speed. So you've got to assume the wavelength's got to change, because if frequency changes, okay, then wavelength's got to change with it. So let's do this in a different color so that you can see it. Okay, we'll do this one in purple. It's twice the frequency, which means I've got to do this. Yes, I've got to get 2 waves in, and that wasn't it. Sorry, just got to remember, I'm doing 1.5 times the frequency. Got to go up and down, up and down, up and down, and this one is sort of there. Okay, I've got to get in twice as many waves. Okay, so things don't quite line up anymore because my frequency has doubled. So I'm going to get crests when I had troughs. I'm going to have troughs when I had crests because the frequency has changed. Okay, wavelength has got smaller though. Now, I put this one in deliberately. It says to you, a wave with half the wavelength. Well, actually, I'm hoping some of you realize we've actually just drawn that already, because my wavelength was from here to here, and now my wavelength is from here to here. It's actually half the distance, because I'm getting twice as many waves in the same time period. So your frequency is doubling, which we did earlier, so your wavelength halves, okay? Now, on a test or an exam, okay, it's a bit of a trick question, you would label this as wave 2, and you'd write it so your teacher can read it, as wave 2 and wave 3, okay? Wave 2 and wave 3. It's a little bit of a trick question there, okay? Now what I want to do, because it's getting a bit messy, is let's, oh, if I can find them. The eraser's gone on holiday. Oh, no, oh, there it is. Let's take these ones out and make it a bit bigger. Okay, so let's take those out so you can see the next one a little bit easier because it's got a bit messy. Okay, so last one. A wave traveling, now watch carefully, at the same speed with twice the period. Okay, now that one's not as simple as it looks because we go, ooh, okay, hang on, wait. Now we're going to think logically about this. We might have to think through a bit of an equation here because we've said, and we worked this out last time, that speed is frequency times wavelength. We're not dealing with that. But speed is also equal to wavelength divided by period. Okay? Now, speed is constant. I'm making my period twice as big. What do you think needs to happen to your wavelength? Because we want the same value. Okay, so I'm hoping you guys realize that it means that I'm going to have twice the wavelength as well. Okay, so if I increase the period, which is the time taken for one wave, the wave must get longer. So when I draw this one onto my wave, it's not going to do this. It's got to go to the same height, and it's going to do that. Okay, so instead of having two waves in the time, I'm only going to have one. Okay, that's the only way I can travel at the same speed because I've made the periods longer. Okay, so it's got to be a bigger wave. Okay, you all follow me on that one? That was a bit mean. Let's do a calculation, they're far more fun. So, here we get a typical type of calculation. It says to me, a fly, and yes, grade 10s, I'm afraid you're going to have to get used to these. We do tend to give rather silly examples. A fly flaps its wings back and forth 200 times each second. Calculate the period of a wing, that should say wing flap, not a wind flap, okay? So that's wing, okay? Sorry. That's,
you're an English teacher too.
Yeah, I stick to my strong points, which is science. Okay, so flaps its wing back and forth 200 times is why it makes that annoying noise, okay? Because it's so fast. This 200 times each second, I could have written that as 200 times per second. And if you remember what I told you about 10 minutes ago, I said to you frequency, its units hertz, means per second. So I've given you frequency. Okay, so in this question, my frequency is 200 hertz. It's been given. That was the trick in this question because what do they want you to calculate? Period. T. Okay, so if we're going to calculate period, we said period is 1 divided by frequency. So that means it's 1 over 200 and we get 0,00, that's right, 5 seconds. Okay? Tiny, tiny, tiny frequency. Sorry, period. Which we expect. That's very, 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 very fast. Okay, 200 times each second. So if we make that in terms of in a minute, it's 200 times 60. That's 12,000, 120,000, something like that. That's very fast, okay? We expect the period to be very, very small. So the relationship you should be getting from this is big frequency means a small period. A big period would mean a small frequency. They're almost like, you can almost think of them as being inversely proportional, or they're the opposite. If one's big, the other's small, okay? Or the other way around. You guys okay with me still? Okay, move on. All right, so we have another question, okay? And we have 2 to go, one more after this, okay?
And Tracy, what I quite like about it when mind-setters do see these questions on their screen, sometimes what they start doing is answering the question, actually start posting the answer on the page before the teacher even gets to the end. So guys, if you are a smarty pants and you do have the answer, don't be afraid to shout it out on our Facebook page.
I like that. I prefer them to try work it out on their own first anyway. So that's
cool.
Brilliant. Okay, so a particular string is vibrated at a frequency of 10 hertz. Now, grade 10s, what I'm doing when I'm underlining stuff, this is what I tell my own learners to do, because a lot of the time the problem isn't with the maths, the problem is you don't understand the question. So it's all about getting the information out, okay? So it's vibrated at 10 hertz. It has a wavelength of 0.25 meters, and then it says determine the speed. Now remember I said to you speed and velocity are interchangeable, so they mean V, all right? Another good thing to do, which I'm sure you've seen me do already, is we write down what you were given. So frequency is 10 hertz. My wavelength is 0.25 meters, and I want speed. Okay, so we go, oh well, now I've written everything down. We can do this. This is straight substitution. Velocity or speed is frequency times wavelength. So it's let me make sure I put it the right way around. It's 10 times 0.25, and it gives me 2.5 meters per second. This is quite a slow wave. Okay, 2.5 meters per second isn't actually very, very fast, but it is vibrated on a string. So this could be something like the string of a guitar, okay, or a violin, a musical instrument. I think to get a frequency of 10 hertz on a skipping rope would be quite difficult. You'd be really, really fast for that. But for a stringed instrument or piano, inside a piano, that's also a really nice one. But it's 2.5 meters per second, okay? I hope we're ready for the last question I have for them, and then we can get to their questions. Okay, a microwave oven. You all know what those are. And it produces, now watch what's happening here. Radiation with a frequency of 2,450 megahertz. That's what the M stands for. And a wavelength of 0.22 meters. Now, when I was calculating this, I actually realized I have a feeling I've got the wrong value for the wavelength of a microwave, but it doesn't actually matter. We can work it out without that, okay? And then they want, what is the speed of the radiation? Why did I put this question in? Not because of the wavelength, not because you haven't done a speed equation yet, but because of the 2,450 megahertz. SI units, grade 10s, are very, very, very important, okay? Frequency must be measured in hertz. Hertz and hertz alone, which means if I've got megahertz in the front, it's a prefix, okay? It's a way of us, instead of writing out all the zeros or whatever, it's a way for us to make it easier. But we can't use the megahertz in our calculations. So, my frequency is 2,550 megahertz. What does that mean for us? Well, there are 1,000,000 hertz in a megahertz. That's 10 to the power of 6. So we need to times this by 1,000,000. Much easier. We're just going to take the number times by 10 to the 6. So you've got to learn how to use your calculators for this. My wavelength is 0.122 meters. That's actually quite small for a wave of this sort of frequency. Okay, now we want speed. So this is actually quite nice because we get here and we go, well, velocity is frequency times wavelength, and my frequency is very big. Please, grade 10s, on your scientific calculators, you have an exponent button or a times 10 to the power of x button. That's the one you want to use. Okay, so you would put 2,450, press that button, then put a 6. Don't go times 10 and then put the 6, because you'll end up with an answer that's too big. Okay, your calculators are designed to do this sort of calculation for you. And what we get is 2,99 times 10 to the 8 meters per second. And actually, that's perfectly acceptable. I'm sure some of you are looking at that going, that's ridiculous. It's a huge number. It is, but it's actually almost the speed of light. And that's fine because microwaves fit into the electromagnetic spectrum. So I know looking at this that this answer is fine because a microwave fits into the electromagnetic spectrum which travels at the speed of light. So I'm not worried about it. It's not quite the speed of light, but that's okay because it is in the air around us, so that makes a difference. Okay? And that's all I have from my questions, Indiana.
I think what we're going to do is we're going to go to an ad break. I'm going to have a look through all of your questions, and then Tracy and I will pick and choose. Guys, don't forget we are having our question session the last 15 minutes of the show, but that doesn't mean that they should stop coming. Keep them coming, keep them coming. And we'll see you now after the break. Hi guys, and welcome back. Can you believe it's the last 15 minutes of our show? I know I can't. Guys, we don't have that many questions on the page. I do have a question from Kanye Sile, which I think we're going to go over.
Excellent.
Are you excited, Tracy?
Always. I have questions and they're maths related to me.
Yay! Okay, so should I get on to this question now?
Yeah.
Okay. This is from Kanye Sile. Okay, so lady, I hope you're watching and you've got your pen and paper out and you're ready. So, the propagation speed of a certain wave motion is 8 minutes per second? Meters per second.
Okay.
Oh, sorry, Tracy.
That's okay. Minutes per second sounds good.
If the wavelength of the wave is 400 meters, what is the frequency of the wave?
That's brilliant. I actually quite like this question. Now, I hope you all saw that, guys, as I was doing it, is while Indiana was reading the question to me, I wrote down the information, because obviously I don't have it in front of me. So they said to you that it's moving at 8 meters per second, it's 400 meters is the wavelength, it's a very long wave actually, it's traveling quite fast, and they want the frequency. Nothing different from what we did before the break, but what that means is frequency, now it's about manipulation. And I do suggest, guys, that you write down the equation as it's given to you before you do your substitution. Okay, do your substitution, then manipulate, because if the maths is a little shaky, you're going to lose marks for a silly reason. So your speed is 8, okay, we don't have frequency, and we want the wavelength, which is 400. And now all we have to do here is manipulate, and I'm afraid I actually am going to have to use a calculator. My math isn't quite that good. But what we would do is we're now going to divide both sides by 400. Okay, so essentially that means my frequency is 8 divided by 400. And if I do it on the calculator, I get 0.02 hertz. Now don't forget to put in the units, okay? This would only be worth 3 marks, and you would lose one of them by not putting in the units, okay? So I hope that helped.
I'm sure. Yeah.
Do we have anything else? Or
okay, quiet today? So that's when I did a little bit of a refresh. Guys, I hope you have sent some questions through.
Yes. Well, actually, while you're looking, Indiana,
okay.
I'll just add to this.
Of course.
What they could have done as well, Kanisile, is been a little sneaky and gone, well, what's the period of the wave? Okay, so we've now worked out the frequency, which is quite nice. So if we wanted to now work out the period, which we can do, we would then go, well, I know the frequency, and we'd say, well, period is 1 over frequency, okay? And we know that's 0.02. Now I'm going to have to do that on my calculator too, because I can't do that in my head, and we get 50. So that's 50 seconds. That's actually quite incredible. That means this is a very long wave, okay? At 400 meters for a wavelength, it's probably a water wave, actually. Yeah.
Okay.
Yeah.
I've got, let me just have a look here. I just thought it was really funny on Twitter. I think Mbusa said, Indiana, do you guys know how much you're helping us?
I'm so glad.
So I was wondering, is this a question? Mbusa, why don't you tell us how much we're helping you? Okay, we've got another question. Let's have a look. Okay, this one is from, okay, let's go, Julio. For the graph question, the particles are A to 1. I think it's either a 1 or an I, and the distance between each particle is 0.055. The time.
Did he send you the diagram?
Yes. No, he didn't send me the diagram.
See with
okay, guys. For those kinds of questions, we need the diagram.
Yeah, because it's guys. It's just because you can describe the question to us, but if it's not from, for example, the free science high school textbook, which we are using as a reference, and you're welcome to send those questions in, and I've got that. It's actually very difficult, Okay, and if you are taking it from your textbook, I need to, I mean...
Even take a picture with your
just,
phone.
Yeah, use it on your phone,
Yeah.
and then I can quickly have a look from Indiana. Just when it comes to the graph things, it does become a little more difficult because I think they're probably asking them to replot and look at distances, but without the diagram,
Yeah, exactly.
doesn't really help us, unfortunately.
Okay,
Yeah.
Mafahara said, if we are given frequency and speed, we determine the distance and how?
That wavelength, it all depends on what they ask you, okay? So sometimes what they'll say is that they'll give you the speed and they want to know that's wavelength, okay? They'll want to know the wavelength because remember, speed is frequency times wavelength. So the distance they're going to be looking for will be your wavelength distance. Okay, so it's the same, it's just a manipulation of what we've done so far.
Okay, and
Yeah.
Anele wants to know, how do we calculate the pulse length?
Pulse length is your wavelength. Okay, that was a good question. I didn't spend a lot of time on pulse. When they're looking at the pulse length, they're looking for the wavelength. All right, so it's just, instead of looking at a whole bunch, because remember with a pulse, it's a single disturbance. So we would have a pulse, and then it would do this, and then it moves on, and it does that. So you would be looking at the distance it travels in a certain period of time. So they would need to give you velocity, and they would need to give you how long it takes to move the distance, and then you can work it out from there, and you would use speed equals distance divided by time. And sometimes they'll put it on a graph, and then that would be literally the distance that you would measure on the graph, okay, depending on what they give you, and then they'd have to give you information on that.
Okay. I think we've got enough time for one more question, and this
Yeah.
one's from Sianda, and it's a nice working
Yes.
out question. I know you like those. Okay.
Yes.
So from Sianda, and Sianda says the wavelength of a wave in the ocean is 10 meters.
Okay. So
Yeah. Okay. And if a crest moves past every 2 seconds,
Okay.
how would you calculate the wave speed?
Okay. Nice question. Okay.
Good one, Sianda.
Very nice question. So,
And you've got 5 minutes to answer.
brilliant. Okay. Here's your. Let's make that our point of reference. Okay. So I'm going to explain to you what the information is given to you, and they say to you that we have a crest, and we have a crest, and they say if you were standing over here with my little stick man, and a crest moves past you, he said every 2 seconds.
Let me have a look. Every 2 seconds.
Every 2 seconds. Okay. So here's the first crest. 2 seconds later, there's the next crest. So the time it takes to go from here to here is 2 seconds. What have they actually given you? They've given you period. They've told you period, okay? Now, there's 2 ways you can work this out, which is actually really nice, and it depends on how they ask you to answer it. If there's no method stipulated, you can do whichever way you like, but sometimes they'll say use the wave equation, so you've got to be a little more careful. But I know that the distance from, I didn't mean to do that, distance from here to here is, let's actually put it on so you can see it, 10 meters. So what they've said to us is the wave is moving 10 meters in 2 seconds, so I could do that speed, which is distance divided by time, and I'm happy to say I can do this one in my head, okay, is 10 divided by 2, so that's 5 meters per second, okay? But if they'd said to use the wave equation, now our life gets a little more difficult because the wave equation says that I need to have frequency. We've just realized that my period is 2 seconds, so I need to work out the frequency. Remember, frequency is 1 divided by t, so that means it's 1 divided by 2, so it's a half. 0.5 hertz. We put it into our equation, and lo and behold, look at that. It's exactly the same value. Either way, okay? And my suggestion, draw a diagram, okay? Even if they are as ridiculous as mine, draw a diagram, because drawing a diagram it gives you an idea, you can picture it. Okay, and a lot of the times it's not the maths that's the issue, it's being able to picture the situation. Okay, hope that helped.
I'm sure it does. Okay, I think we've got about 1 minute left. That means I can ask you one more question. I think this is a short one.
Yes.
From Tumi, can you place the wavelength on any trough?
Yes, we've just chosen the crest as our starting point, but remember I said to you wavelength is the distance between 2 points in phase. So it could be here. That's also a wavelength. Absolutely. As long as they're in phase, we can put it anywhere. It's just we tend to put it on the crest because that's the top.
Okay.
Yeah.
Fantastic. We've got 1 minute. Let me know if you can answer this in 1 minute. How do you calculate the phase difference from Valentine?
You don't have to do phase difference.
Okay, so grade
That's
10s.
us. It's not even in grade 11 anymore.
Okay.
But thank you. It's a good question.
Okay, fantastic. Okay, guys, unfortunately, grade 10s, we have come to the end of our show. Grade 11s and 12s, I hope you've been watching too. Grade 10s, I think you're fantastic. Don't forget, we will be choosing a winner on our page tomorrow for the Casio calculator from this session. Guys, grade 10s, thank you so much for an amazing lesson. Grade 11s, make sure that you tune in to the next show. I think we're talking about gases. Guys, let's learn more. Let's learn extra. Grade 10, see you same place, same time next week. Bye.